we are finally at the culmination for a driven oscillation circuit. Okay, this time we're going to put all three, resistor, inductor, and capacitor, in series with an AC battery. Okay, so again, looks like this, and a very simple circuit with an RLC. The order of these doesn't necessarily matter, but I'm just drawing them in order. Okay, looks like that with a current going around, right? At some time, I'm saying it's going clockwise around the circuit. Again, this current depends on the resistor, inductor, and capacitor at the same time, right? Simultaneously, they're all affecting the magnitude of this current, okay? So this is the same current value for the entire circuit. So this generates, or we can write down rather, a Kirchhoff's loop equation, starting with the EMF and then subtracting all of the voltages for the circuit elements. So we have this, right? And thus, the EMF varies in time. We can write it like this, right? And now, taking the V's to the right side, the voltage across the resistor can be written as IR, and then plus the voltage for the inductor, L di dt, and for the capacitor is Q over C. Okay? And I'm going to rewrite the right side just in terms of Q. Okay? So copy that back down. And I'm going to put the inductor first. So L d squared Q over dt squared plus R dq dt plus Q over C. All right, now this is a scarier differential equation than what we've encountered previously. All right, now we have a second, a first, and a zeroth order term with which to solve. You can do it. It's doable. It's solvable. It's not the most fun to do, but if you want to pause the video now, take the next 2 years or so to solve it, come back and see what you get, you can. Or you can keep watching and see how you can solve this for current using simple geometry and Pythagorean theorem. All right? So let's do it that way. That sounds better. To do that, we need to keep a couple things in mind. The first, I'm going to draw it here. The first is that the EMF is a function of time and has the form that I wrote above. Okay? It looks like a P, but it's a driving frequency. I'm just making it worse now. Secondly, the current, I of t, is this form, right? The general form. There. Notice that the current has a phase angle, right? A non-zero phase. It will have a non-zero phase from the EMF because it has an inductor, capacitor, and resistor all in series affecting it, right? It will never have the same phase as the EMF, okay? So we have to have that phi in there. Secondly, we need to remember how the current and voltages through each RLC element related to one another. So the current compared to the voltage for the resistor had an angle of 0. They were in phase. The current compared to the voltage for the capacitor, that phase was equal to negative pi over 2. Okay? And conversely, the current compared to the voltage across the inductor, that phi was positive pi over 2, right? And so lastly, that leads us to our memory aid, Eli the Iceman, just like in Top Gun. Eli the Iceman, right? And again, this says that for an inductive load, the current, right here, lags behind the EMF. That's the same thing as saying the EMF or the voltage for the inductor leads the current. For a capacitive load, the current leads the inductor, which is the same thing as saying in a capacitive load, the voltage for a capacitor lags behind the current, right? So let's keep that in mind when graphing them out. In this space, I've conveniently set aside. Okay, so I'm going to do, let's see, I'm going to draw the current first. I'm just going to choose a random position. So that's the that's the only current in our circuit, right there. It has that amplitude and that angle in time, okay? The angle, by the way, I should mention is, oh, I forgot T. The angle, by the way, is that omega T minus phi. That's the angle for our current. And so that is right there, omega T minus phi, right? And we know that the voltage for the resistor has to be in phase with that, right? So thus, I'm going to draw it right there. VR is in phase. The amplitude isn't necessarily the same. I'm drawing them differently so you can see them, right, that they're separate. But that's in phase right there where the current is, right? So that angle is the same as current, whatever it is. All right. Next, let's graph the phasor for the capacitor, right? The voltage for the capacitor. Let's do that in blue. So going down to our memory aid, Eli the Iceman, for a capacitive load, right, the EMF or the voltage VC is lagging behind the current. And so, whoops, I didn't specify that these are all moving counterclockwise at the driving frequency. That means that, well, the voltage for the capacitor is right there, right? It's behind the current by pi over 2, a right angle. Let's do the inductor next. I'll do that in green. Looking down at Eli, the voltage for the inductor is in front of the current, right? It leads it. So that means that it's over here. Now, I'm drawing these at different amplitudes for a reason which will become apparent shortly. So that's VL. Also, a difference of 90 degrees, okay? All right. I think I have everything. So let's copy this down. Let's transfer this over. I love this feature, by the way. Copy, move to the next slide, paste. All right. All right. Now let's take a look at how that relates to the overall EMF, right? And get a single expression for the current in the circuit. So we have 4 phasors written down here. Where's the EMF phasor? Where is that arrow pointing? Well, if you remember, the EMF is separated by the current by phase angle phi. Okay? And so actually the EMF, we can draw in purple, is somewhere over here. So thus, this is the angle phi. That's the difference in between the EMF and the current. Okay? Okay. Stay with me. Now, let's regraph. But before I do, I'm going to take this blue VC arrow and flip it. Right? Actually in blue. I'm going to flip it. So let me... keeps the same magnitude. Right? So this, see, that's... So in black here, that is VL minus VC. That's what the arrow is in black. And now that is what I'm going to graph over here. right? So we have VL minus VC. That's the difference between those two voltages, right, as a phasor diagram. I'm going to keep the phasor for the resistor, right? That will not change. And if you notice, these are exactly perpendicular to each other, right? They're at a 90-degree angle. And I did this to have the ability to do the Pythagorean theorem. So now, let's change that angle a little bit. It looks like, whoa, looks like my EMF will be on the line. I don't want that. So let's do red. There we go. Now in purple, we can do the EMF. Should be a little bit longer. Sure. There we go. What does this look like? The EMF effectively is the hypotenuse of that triangle, right? With sides A and B of V, of VR, and then VL minus VC. So that's a right triangle. And the angle right there is phi. Right? So what we have, I'm going to transpose that down, is that there is R, and then in black, VL minus VC. So that is our right triangle. Whoops. And this angle here is phi. And so now it's just a matter of using the Pythagorean theorem. Right? So let's do that. So a squared plus b squared equals c squared. So I'm calling that c. A, I'm going to do VR plus our, there we go, our b. A squared plus b squared. Okay. Now I'm going to write this in a little different terms. The voltage for VR was IR. Right? Actually, whatever. And for the other one, for VL, remember, it was actually I times chi L. And then for VC, it was actually I times chi C. Nope, I'm doing that wrong. Take those squareds out. There we go. Remember, these are the reactances. Right? They're the AC equivalent to resistance. Okay? And now I'm going to take out the I and solve for an expression for just current. So that means we have to take all that and divide it through. Remember that chi sub L was equal to omega times L minus chi C was 1 over omega C. That's squared. And now to get value for the current, we just take the square root of both sides. Right? Actually, E goes away too. Right? And this is our expression for the current. If you want to take that one step further, this epsilon on top is actually a function of time. And on the bottom, we have the total effective resistance for the circuit, which can be written like this, 1 over omega C. It's a lot to write here. Right? And we give this, right, the stuff inside this square root, a name. Right? We call it Z or zeta, which is called the impedance. whoops, the impedance. Impedance effectively means it's the total complete resistance plus reactance. It's the total hindrance to the current flow, right, for an AC circuit. So basically, effectively, we have that, right? And that's our value for a current, right? If you wanted to find phi, that angle, right, find phi there, well, that's easy. It's just tangent of phi. Well, tangent is opposite over hypotenuse. Well, that's simply VL minus VC, you know that, omega L minus 1 over omega C divided by, opposite over adjacent, over there, that's tangent, right? And that's a way to find the phase constant between everything. But this is the total expression for the current as a function of time in an RLC circuit. It looks complicated, it looks scary, but really if you boil it down, it's just geometry and some Pythagorean theorem, okay? So keep these in mind for solving these RLC circuit problems, right? You'll need to know this tangent of phi expression as well as the various reactances and the total impedance, okay? All right, thanks for watching.